Yeah, welcome back, guys. Another day. So, today I want to go through what we left off yesterday, and it was something about fixing. Yeah, we were jumping into some sort of loop and what's going on there. This is what this is what we were debugging yesterday. So we have some sort of if we run this thing, after we jump into the kernel task, the first task, we are in some sort of loop where we are keep on switching things, but I'm not sure why we are in that loop. But I was thinking about this issue yesterday, and I believe instead of taking the shortcuts, it's better to strengthen the core so we get a better basement to work on instead of having things done badly, I would say. Currently, if we get into our MMU, almost everything is already paged. That was the one issue that we figured out yesterday, that during MMU unit I am setting a page entry for everything that starts from 8000 until next 1 GB. So that's a lot of memory that is set to a block of memory, and I'm setting the block entry here. So everything in this region is already mapped, and during our kmalloc we again try to keep track of pages, and this is the actual function where we try to map new pages in case we wanted it. And we had a loop that was trying to do the same things. I can maybe see it. Table, yeah, you can check this one. So we are simply adding table entries for new pages, but there's one issue that it's possible that we don't even need this. At least in my scenario, we don't need it because we are already setting 1 GB of block, 1 GB of memory as block, and it's already valid. And most of my code, if you remember from the previous examples, previous sessions, our memory is mapped from 0x0002. Where's that code? Let's see. I think it should be inside this. Yeah, so initially this is what we wanted to do. So everything that starts with FFFFF and 000 will be mapped to 00000. This is what we wanted to do, and then we realized that this is not our physical RAM. In QEMU, our physical RAM starts from 8 something, So what we did is the same thing. We mapped everything from this into 8s and offset, and I'm just trying to see that offset. Where is that? Maybe I have added it in linker. It should be in table. Deallocate. Find free. Check if it is free. Yeah, this is our base address. So everything from 0xFFF 1 2 3 4 1 2 3 4 1 2 3 4 shall be mapped into 0x 1 2 3 4 1 2 3 4 800b 1 2 3 4, and the offset stays exactly the same. So everything from here will be mapped into this. And as I mentioned before, this 800 already has some page table entry, so that's exactly why our kmalloc worked, not because this function actually mapped something, because we had this map page table entry where we were mapping new virtual memory into new physical base, which should have broken a lot of stuff, but lucky as it did not break anything in our case, and we just simply managed to get through that day. I guess I have written everything here. See, even that day I knew this fact because I have wrote it like we already have a L1 table used in, we could reuse it until 1 GB. So I knew that there is 1 GB of memory that's already used. Still, I was not able to put together everything to come up with the idea that so this memory must have been already mapped. Okay. Let's just check one thing. 1 GB of memory from 0x80034. What will be the ending address? Okay, so the ending address would be it would be 0xC0000. This would be the ending address. Let's see if our memory falls under that. Where is it? Just saw it right now. Oh shit. Where did it go? Something 800b. Okay, it's here. 800b0. 1 2 3 4. So So it definitely, this address is definitely within this range. So that's exactly why we have all the entries mapped properly. Yeah, so it's a really big bug. Or maybe what we can do is that we can change this physical address to start from here, so that we won't have a page table entry. That should be good, right? Instead of trying to meddle with the existing code that's already working, why not just okay, let's start from here. So I'm pretty sure that this address is not mapped, so if we try to compile it, we should get some failure. Not from here, I was expecting. Okay, that's just that. I have to comment this out. Probably we'll have to uncomment this entire part, because right now we are just going to get a page false. Yes, exactly, nothing happened, because as you can see, in our example we are supposed to allocate memory and try to read and write to them and print them. And so here we are allocating it, we read and write, and then we print stuff. And this should not work because there's no page table entry. And let's just confirm that. Let's rm commu and run it, kill it, and then take the final 100 bits. I think we are getting into I guess we could do one thing. Is it FSR? FRS? I don't remember the name. Let's just open the file and check it. Where's that? Not sure. Maybe it's because we have handlers enabled, so we are just getting into the handler instead of throwing that as an error. Maybe that's what is happening. Because this is where the looping starts, and yeah, it's definitely possible. And from the example we can tell that that page is not mapped. So now what we can do is, what can we do? Now let's just fix this part. the one that's supposed to walk. Where is it? It's inside. But I guess the problem is clear here. So previously we had 1 GB of memory that's already allocated, and within this map page table entry we were um, like overwriting some entries with a new base. So let's say we had one page table that is mapped to, let's just write down the bug so it will be easy. Let's say example, let's say this FFF000, and let's say it's 6000, and it was mapped to 0x800 B008. Let's say if it was mapped to this, and in the next iteration if some other new entry was allocated, so this does not exactly map this address to this address, because if you look into the code, we did not do it that way. We were still making block entries. If we open the code and if we uncomment this whole thing and uncomment this and uncomment this whole thing, uncomment it. Okay, so here as you can see, we were going through the number of table entries that we want to map, page entries that we want to map, and inside that, for every address that comes in, let's just write another example. Let's just write another example 4 and let's say 8. So here we'll have 8 and then it's 16. Is it 1A or 10? It's 15 is F, and then I guess I have to put a 10, and then we put 1, 8. Let's say these are the 3 memories that we want to allocate, and we have allocated it based on this. And what we do is just we going to get the first L1's index and L2's index, and we make a block descriptor with this physical address. So we say that everything after this starts from this base address, or everything for this address starts from this base address. So technically this L2 entries will only care about probably, I guess, this. So all 3 values will have the same index. Probably the index would be, let's say, index equal to 3. So we are keep on overwriting this index with a base address. Initially the base address would be this, and in the second iteration the base address would be this, and the third iteration the base address would be this. Overwriting the base addresses. So the issue would have arisen, which did not arise, because let's say we initialized this and then we wrote something to it. We added one entry and we wrote something to it, and then we try to create a new page entry. Now the base address would be overwritten. So we have lost this entire data. So now even if we try to access this, now the initial address was this, it was mapped to this, and in the next step we write something to it, and then we create a new page table entry that is this to this. That would be still the index 3 and the base is pointing to this. Now if we try to read this, read the first address, we would be starting from this base PA, and that is just a disaster because we entirely lost this address. This is what was happening here. And there are some ways to fix this. Either we have to completely change our initial MMU init into page level tables. That is, we have to also add the L3 table, L3 entry instead of making L2 blocks. Or the one that I just figured during the stream, that is that why not just add the next base address, because there's no table entries for this address because we are adding entries for 8000 and 8000 till 1 GB. As you can see, L2 entries have a total size of 1 GB. So anything that starts after that 1 GB, which is C000, should not have one page table entry. So for everything that we do, we just start from here. That's it. So in our case, we have to come down and we need to create page level entries, that is L3 entries. So we have the L2 base, and let's assume that we can just use 1 GB of L2 because we don't want to keep on using more L2 entries, because L2 entry is 1 GB of space. So let's just hard code the L2 entry. If it is not allocated, then we'll add the L2 entry. Let's add the L1 entry once here, because we need to map 0xC1231234 plus 1 GB. This is what we need to add. Okay, so that's good. And adding that is pretty simple. Let's just copy this part. Can just copy this whole thing, yank it, and paste it here. Okay, and we need to do some changes. That is, we need to allocate some base memories. So calculate index of current VA is we need to add an L2 entry. That is all. So let's just say the current VA is FFFFF0, because this is just one time action. So current VA is 0x 1 2 3 4 and 1 2 3 4 1 2 3 4 1 2 3 4. This is our current VA, and everything is just going to be index 0. We don't even really have to. No, that's the issue. I need to add an entry next to the previous L1 index, because the previous L1 index was the one we were using, that is 0x8002 plus 1 GB, and we need the next entry, so the index from the previous plus 1. That would make sense. Then in that case, why not just copy this one? Yeah, I think it's better to just copy this part. Wait, how did this work? It's 82004. One, two, three, 1, 2, 3, 4, 1, 2, 3, 4. This must already have an entry, right? Am I assuming something wrong here? Oh, fuck me. If what I said was true, this should not have worked, because this also falls under the same 8000. I mean, if we could just print this index, we would get an idea of what exactly we are. Right. What printf is available at this level? Let's just print main L2 index percentage L2 index. And you what L2 index. Let's see what exactly are we mapping. Okay, let's just fix this error, and maybe we don't have to fix it. We'll just comment it out and run that code and see what was the index there. Oh, we fucked it up big time. After fucking tail dash in 100 cameo. Why am I catting it? That's the whole performance issue. Wait, what other things did I change? Is there any way to, I didn't put commit anything, so I won't be able to go back to anywhere. So let's just see. What did I add? I have added 2 UART messages. Is it possible to add UART during MME unit? No, that's the issue, because UART init was called inside kmain. Oh, fuck me. That's just sad. Okay, we won't be able to see that indexes. I'm a bit confused. I have a 48-bit VA, so definitely I have the 0th index, because I know I have tried it. And then I have the first entry, that is just index 0. And then I have the second entry. Wait. Maybe it's the other way. I'm starting from... Wait. Where do I start? I'm starting from 39, so it's definitely 0th index. For L1, for L0, I create a table entry that's just L1 base address, and for L0 I create a L1 base, and for L1, which is which is of size 1 GB. I'm a fucking idiot. Why can't I simply read this fact that L2 only has 2 MB of memory? Everything is already correct. See, like we have L1 entry that is of 1 GB, and we have created an L1 entry, and we have added L2's table base address, and then we go to L2. Within L2 we can separate this 1 GB into 2 MB spaces. I was looking into this and I got confused. This is what I should have looked into, and what I said was correct, because here in L1 entry everything is 1 GB, so we have an 1 GB memory location that's already allocated. But if we go into L2, L2 is not supposed to have that. L2 is dividing that 1 GB into 2 MB spaces, and that's exactly why we were able to separate the entire code. We have like some entries like for 8002 one next 2 MB, and then we were able to map 8244 into 9000, which is for UART, and it just works fine, and it has been working for a long time. I don't know why I decided to question this. I think 2 MB is not that bad. We don't really have to. We are not setting 1 GB of block memory. We are setting 2 MB of block memory. This is wrong. Remove the block. So there's only one update that we have to do. Now our array map should be considering one entry as 2 MB. Then we don't have to add the third table entry, or we can add it, but then we'll have to hold lots of tables, because for every 2 MB we'll have to create separate L2 L3 tables. That's just a lot of stuff. So this to-do is wrong. This is just fine, and it's working fine. Let's just write this down, because next time we don't want to meddle with this. L0 we write to index 0. L1 we write to index 2, I guess, because our starting address is 0x8000, and for L2 I think no, even in L1 it's index 0, and in L2 now we are within that. Holy fucking moly. No, this is 1 GB, that is L1, so it should be index 2, because index 0 would be 0x0002 some 1 GB, and then next 1 GB to 2 GB. No, in 1 GB is 4000, so it's correct. So it would be 0x400. and the second index would be 0x 400 to 0x 800, and the third index, which is each second index, that is 0 1, and then we grab the 8 to 0xc00, which is second. So this is correct. Now within that second index we have a L2 table, and that table has to hold this 0th bit. So it's going to be 2 entries, 0th index for base and some address, I guess it's 11 for UART, which is 0x8240. L2 entries are 2 MB blocks. Okay, at least we cleared that part. Okay, so we don't have to touch this, it just works, and there's nothing wrong with that. And one change we have done is that we updated the physical address. Where is that? Physical address to C00, which is good because we don't have to even worry about the MMU's region, so we don't even touch that part. We start from index 3. So let's just say if we go into this, and if we uncomment this, we don't have to add an L1 entry because what would be the table descriptor? L2. No, we'll just reuse the same table descriptor for L1 entry, and for L we'll use the same table descriptor, and it would be, let's just copy it again. I guess we changed some stuff which might confuse us again. Let's just copy till this, and then we'll remove certain parts. We copy this and we remove this. Okay. The fuck happened? My fucking tab just doesn't work. How do we tab in? Is it shift? Okay, that's good. Now we can remove the L0 entry because L0 entry is same for everyone. let's just comment this out. And then we have the L1 entry. L1 entry is supposed to take how many? 1 GB of space. So previously it is L2 L1 index is 1. So in our case it should be 2. No, previously it was 2, so it should be 3 now. Maybe it's better to calculate it so it will be dynamic in a way. But because we start everything from FFF000, we won't be able to do that. Okay, currently let's just write it and add a comment. It should be index 3. What is this? What is this 3? 3 is because we start from we need an example. Example, let's say we access 0xFFF 000 1 2 3 4 1 2 3 4 1 1 2 3. Let's say we try to access this. What has to happen? We go through I think we don't access things like this, because if we go into our kmalloc, we try to call allocate mem and we take the top index and we convert that into physical. And the top index would convert bit index into physical PA. If you see, it's just that physical base page. So it is going to give everything starting from this physical bit page base page. So I think we'll never try to access this memory. We'll always try to access all we have to do is give bit index 0. But yeah, but it's just okay. I think I'm trying to get a hang of it. Hang of what I'm fucking with. So here we will never try to access this, because when we try to allocate something, we are always gonna start from C. What the fuck? We are always gonna start from here. 1 2 3 4 3 1 2 3 4. This is what we are gonna start from. So I think we can use this as the current VA. Yes. And then we find the L1 index for this and create a L1 table. This L1 table will be the constant, because as it will have 1 GB of range. So let's just use this function instead of hard coding anything. Let's just say uint how do I go back? Is it B? Okay, it's B. Uint L1 current VA equal to 0x 1 2 3 4 1 2 3 4 and C 1 2 3 1 2 3 4. Okay, this is our memory. I guess we can put UL unsigned long. Okay, we have the current. Now what do we do? Now we can just call calculate L1 index for current VA. That's it. And it should return 3 and L1 index should be 3 in this case. And we have the L1 entry, and we are setting L2 in that index. We are setting L2 as the base table. Now we want to create a new table, so let's create the new table. Where's the tables? So maybe we could use this table, because this is what we created. I guess we can use this L201 instead of we can use L2 index 3 base. That would be a little more. This is what we use in our malloc. Okay, malloc. Okay, let's use this. If we go back here, we can remove. Maybe we can clear this L2 index, and we can remove this. And if we come back down here and let's add within L1 table, we need to add a table descriptor, which is L2 index base. Okay, so now we have an L1 index with a new L2 table that is set. We don't need this. Now we are gonna, no, we don't map anything here, because in this block we only add a L2 entry. it's an L1 entry, and it's going to be only done once with that global static, because we don't have to keep on creating this entry for every allocation, because this only has to happen once. And we could do one thing. We could just simply calculate this index, and if this index were to go higher than 3, then we can put a stop message, because in future we'll definitely have to deal with this someday, maybe far in the future, but still let's just add that performance degrade here. Yang 1 to 2, and let's put it outside. What the fuck did I yank? Yank 2. If I put 2, it's yanking 3 lines. What the fuck? Okay, so we have this. Let this part run in every example, and we can check if the L1 index is not equal to 3, then UART printf need more RAM, bro. Check this out here. And will return false. Now we have the L1 index, and we can use it here. We don't need this party. Okay, that's good. I think we can remove this too. Now we have some guardrails. No, we don't want to do this to do. That was just stupid of me. That was just stupid of me. Okay, let's remove this command too. I don't think that map is valid. Yeah. Now we are ready to make 2 MB memories, and that's where we have one issue, because all our our allocator only considers pages of 4 KB size, and we have a bitmap array that says, like, if the index 0 bit 1 is set, that means the second page is used. So every bit within our bitmap array is an page, and it's a 4 KB size. That's why we are able to just get the index and multiply it with 4, and we can get the proper address that was used. Because now we have to change that into 2 MB. Maybe what can we do actually? Mm, 2 MB 4 KB is 4096 bytes. 2 MB is how many bytes? Oh, that's a lot of bytes. Maybe we just have to divide this by let's do some tinkering. If we go by 3, mm, 2 MB equals we can't have 2 in names. Okay, MB divided by 4096. Fuck me. Okay, so it's perfectly 512 entries. So with one block, with with one entry blocked, we can have 512 bits. If we allocate one page of 2 MB size, if we allocate one page of 2 MB size, if we allocate one page of 2 MB size, then it is like allocating 512 4 KB pages. So what we have to do is pretty simple. I think as long as the total is how do we calculate the current address? We take the VA plus, what does this mean? Virtual address plus 4096 into I. Yeah, that's true, because what I'm trying to do is that because we have the starting address here, we have the starting address and we want to allocate, let's say, 3 pages, then we first allocate the page virtual address plus 0, because 4096 into 0, and then VA plus 4096 plus 1. So that is fine. It should work perfectly. But what we have to do is We have to allocate 2 MB of blocks. In that case, maybe it's just better to create new tables and add the L3 block. How do we approach this? Should we just keep it as 2 MB, or should we allocate new tables for what do we do? If we were to keep it as 2 MB, how would this example go? Here we have to, if we allocate one page, that would mean till next 512 entries are already allocated. Our next 512 4 KB pages are already allocated. Okay, that's fine. So if that's the case, then what do I do? Then I just have to check if the memory comes within this 512 block. Also we allocate mem, which would give the total allocated. And then we take the first index of it and we do all this nonsense and we allocate that page. This looks solid. I don't want to change this. I think it's better to just add the okay, so let's just add the page table entries. Make table descriptor can be reused, right? I hope so. Because table descriptor is 0 and 1, I guess. No, it is 1. Table descriptor is 1 and 1. Okay, let's just try it. Nothing wrong in trying. So our L2 will always be the same. It's going to be L2 index 3 base. Within that, every entry is going to be another table. We don't want to do anything with the L1 entries. We'll remove this entire thing. Now we have L2. And L2 index would be we have L1 index already. have to calculate the L1 index. L2 global VA. Global VA. L1 global VA. So here we can say current VA equal to VA plus this, and we find the L2 index and make a block descriptor. Instead of that, we create a table descriptor. The fuck? Make table descriptor. Make a table descriptor. Now we have to create a new table because every wait, let's picture it. Now we have 2 MB and there is 512 4 KB blocks. So we create a page and we have to store this somewhere. Where can we store this? Yeah, because every index within this table has to have a table entry, and the table should be of 512 size. Only then we can have L3 tables. I think there's no other way. Let's just create some static. I guess we initially put our tables under linker.ld. This is where we store our what's that? Main bitmap array. I guess we'll have to store more. Let's just align this. block L2 memory start. Okay. It should be fine, right? Because one entry should have 4 KB. I think it should be fine. Let's just use this. Yeah, this is where we take that as a void pointer. And where do we define it? Maybe inside MMU hutch. Yes. Extern event. Okay. We don't need the end. Maybe we need the end. I don't know. We don't need it. Let's just so we take block memory start plus we need 512. We need 512 entries. So it's 512 plus I plus into I think it's correct. What I'm trying to do here is that we have this memory location and we need to dynamically create new tables of size 512. So we have this location and to create the first table we take the memory plus 512 into I. If it's the first location it's just 0, so we get this. And if we want the second table, that's location into 512 plus 1, so after 512. I think it should work. So this is our table. And we set entry into current L2. What is current L2? Current L2 is the base of the table, and within this index and this descriptor. I think it's good. We don't need this entry. So what happens is for every L2 index we need to create a new L3 table. So we use the block plus 512 as the logic to find the index. And we create it, nothing much. And this should be inside here. And the index is not this, it should be L2 index. Why is it L2 index? Because the current VA L2 index is the index within this table. This L2 table will have 512 entries, and every entry should point to a L3 table. So we find that index and we create that table, that is using L2 memory start plus 512 plus that index, and then we set the table. Okay, this is correct. Okay, L2 index and PA we don't have. Maybe we'll also L3 table is L L3 table address. You want 64 L3 table address equal to I think we will get some compiler error. In case we might need to convert this into void star. Why do we have to convert it into void star? Let's just put u in 64. If 512 into 512 is enough, I guess. Five and five. If everything goes well, which is not gonna happen, but at least we'll hope. Oh shit, we fucked up somewhere. We tried to allocate, which is L2 index, and PA is this. Why did we try to allocate the PA? Wait. I just remembered. We have added L2 table, and we set that into L2. But now we also have to add the L3, right? Because inside L3 we are supposed to do some stuff, or actually make the table block descriptor. So let's just copy one block descriptor code. Do we have a block here? Yeah, we have it. Let's just copy this. Did we cut it? Hopefully we didn't. Okay. Now we need to calculate the L3 index. I guess we added the L3 helper yesterday, and we have to put the current VA. And it's L3 index, and it's L3 in descriptor, which is just PA. And we write into L3 table, which is L3 table address. Okay, if everything goes well, this time we should have something, at least a different error. No, not in different error. What are we trying to do? We are trying to allocate 4 locations. We are trying to allocate 4 pages, and for this VA, and let's just kill this. Commute. We don't need this to do anymore. L2 index will be 0, or will it be? I don't know. Calculate L2 index. We find the L2 index for the current VA. And what's the current VA? It's the VA plus something. Okay. Oh. Sometimes we just write shitty code and it fucks us so hard. Okay, at least something should have changed. We have I, which is less than, and do we have anything else? Nothing much. In L1 base, in L1's index, we set this table descriptor for L1 table, L2 table. L1 index is 3, if not we would have gotten an error. And we find the L2 index, we create a new table, L3 table, starting from this address plus 512 into index, and then we I guess we need the current VA printed. That way we would get an idea of what the fuck happened there. VA. Okay, let's see. Why the current VA did not update at all, but we went through it 4 times. Or did it update? No, it did not update. Let's just put one UART here and see. Allocated maps. Let's see. Okay, we do say that we allocated maps after that, so definitely we are iterating over it 4 times, but the current VA stays the same. Why is that? Let's just check the index. We are printing current VA, right? Oh, no. I'm printing VA. Current VA, okay. Stupid fuck. Okay, so that part is working. We have four indexes. We start that, we find the L1 index for that, and L2 index for that, and we create the table. And we create the L3 index. Let's just check L3 index. Let's see if the L3 index makes any sense. So L3 index has been updated, because for the first one it's 0, the second one it's 1, and the third one it's 2, and the fourth one it's 4. So we are updating it correctly within the table. We set it and okay. Maybe we have to set that entire block to 0 first of all. That would be good. When we call it the first time, let's go through that entire block and int I equal to 0, I less than 512 into 5 I plus plus block 0. You can try this. I don't know if it'll work or not. Because we might have to zero out stuff. I think we are still zeroing out. Is it that big of a location? Then maybe something is wrong. Let's just put 10. And put 10 here. Okay. We zeroed out it and we got the pointer, but we still we have an error. Okay, now I guess we can check the Kernel logs at this point. Kernel logs used to give me good errors. Now it's not giving me any error. Let's see. It's still the same fucking thing. It's just so fucking annoying. Did I change anything in my build? No, it's the same. It's all. It should work. It should work. Maybe we'll remove all the handlers. I think it's getting into this sum of the block, and it's going into this not as a skull or something. Put here it here, so we'll never have to worry about that. Okay, now we have the exception. Now we can at least do something about it. Okay, perfection. Okay, we have the it was FAR. Okay, we have the error for this address. This address does not have an which it does not have 47. Does that mean it does not have L3 address? I think so. Let's just, because we added level 3 table just now, so probably that's where it fucked up. Because 4.5 is L1, so 4.6 must be L2. Yeah, it's level 3. Oh, that's fine, that's fine. Okay. What we can do is we go into our contar. Where is it? Decimal to hex. Where is my decimal to hex? You piece of shit. I asked decimal to hex. Okay, this is the address. Okay. We just have to fix this third part. We create a table descriptor. And there's some things that we can confirm whether table descriptor is different for L2 index, because I'm using the same helper. Do we have to shift it a little bit different? have the L2 index, which is just 0. I don't know. L2 index can be anything because we can throw in anything after this address. And then we create a table with that index. We make a table descriptor for that address, because this is the address that we want to store. And then we set the current L2 table entry, current L2, and the index is wait, I think yesterday we also saw one more thing that was a bit different, is that for L3 a block descriptor is 1 1, it's not 0 1. Yeah, this is the issue. L3 block we have to write that helper. Make block descriptor, we copy this. Oh, sometimes my VI just fucks with me. L3 block. This one, and we have to set 1 and 1. Base address, we have base address, and how do we make a table descriptor? I think if we just make it as a table descriptor, it should be fine. What's the difference between the table descriptor and this? What is this? 1 10 times, and 1 0 times. One times. Okay. I think we just have to add DAC table here, because that then it means we have 0th bit as 1, first bit as 1, and for some reason we need the 10th bit as 1. I don't know if we need that, but let's just keep it as it is. And then the output block should have the full address. I think we don't need to do any we just shift it right as to 12. That's all. If we shift it to 12, this is left shift, right? So we are just moving everything to left to the 12th bit. That is probably this bit. I guess so, because this is the 47th bit. In other cases, we also have to only set the upper block and we don't have to care about these blocks. So we needed some extra. First of all, we remove the lower half, and then we right shift everything to the end, and then we left shift it. But we don't have to do that shit here. We just take the physical base and we push it to 12th bit. I think it's good, but I did it for this. Okay, and then let's just change it this to L3 block. That is my L3. Oh, let's see. I think if it doesn't work, then probably we just have to fix this alignment properly. And what's the error? It is still the same. No. It's ESR 4.3. We have a different error now. What's 4.3? The code for 4.3. Four three is translation error. Then the last time it was 4.7 and it was still translation error. But how? Wait. Let's kill this. Remove this file. Get a fresh start and check the logs now. This is the faulty address. That's not the faulty tweet. What else can go wrong here? We have make table descriptor. Let's try to add a normal address here just to test if things are just working or we are fucking it up somewhere. Let's try 9. No. Let's try 8 and then 9 and then 10. It's A, I guess. Then A is 10 is A and 11 is B. 12 is B. Okay, let's try 12. Let's try this. And let's try the L2 base address as L3 index 0. We make a table descriptor for that table. And then we set the entry, table entry, into L2 index. And then we calculate the L3 index for this VA. And we make a block descriptor with that PA. And store it in the L3 table. If my L3 table was the issue, this should go away. So my L3 table wasn't the issue. Okay, so if that's not the issue, then the only possible that could thing that could go wrong is this. Maybe we don't need this. We check this part, and we also have to check confirm this part. That did not work, so the final thing that we can test is what exactly should we page descriptor is have I used this anywhere? Not. Nope. Physical base, and I right shift it. That's left shift, so the address should start from this. Then should I left shift? If I left shift, maybe I have to. In this cases, what am I doing? I'm taking a physical page and adding it with FFFF. And then right shift it to 12. Okay, I'm removing the no, left shift it by 12. I don't think I have to do this operation because I need the entire bits. I guess I just have to put a print message there and see what is the actual thing I'm writing into. Wait, what am I trying to do in my main? I'm just trying to Probably write something. Get the pointer. Yeah, I'm trying to write something here. Into that location. And it's stuck there. Yeah, it's simple. We just have to figure out why we are not able to make the block descriptor. Make the table descriptor, and we make the block descriptor. If we do this operation, what will happen? I guess this is just getting out of my hands. I guess also it's been 2 hours. I'll try this later today. Yeah. This is what I need to fix. Let's just put a to do here. To do fix why we are not able to make the block disk in page in L3. Okay guys, bye bye, have a good day.